Thank you. Yeah, I'm very impressed by your seminar attendance on spring break. I feel like it's better than many seminars I've seen not during spring break. So thanks everyone for coming out. So I want to talk to you about, I work in the area of large language models, machine learning, and I want to talk to you about LLM reasoning, and particularly the advances that have come up in LLM reasoning over the last several months, past year, and where I see this going in the future. So just to kind of clarify what I'm talking about, in 2026, we have sort of higher expectations for AI systems than we've had in the past. We expect them to be able to reason. I'm not just going on there and asking for something like, when was Abraham Lincoln born, or these very simple factual queries. I can go to a site like ChatGPT and I can say, I'm planning a workshop. I got to schedule all these talks and everything. And, probably almost all of you have tried things sort of like this. And, you can see that these systems are pretty good. And what I like about this example, first of all, it's evergreen for academics who are trying to plan workshops and things like that. And second, the system did a little bit more. It added a welcome and opening remarks that I didn't necessarily ask for. So, you can decide whether or not that was the right thing to do. But there's this idea of taking my inputs, synthesizing the information I've presented, and then reasoning about it. And so these are two capabilities that I think are really important and kind of underscore a lot of what's going on with the advances in large language models. So we need to extract some kind of information from the context and then synthesize and reason about that information. Now, extracting information from context, one problem that my group worked on for a number of years was text summarization. And back in like 2021, 2022, the hallucination problem was really, really bad. When models would try to summarize a document, they couldn't really crank out a 3-sentence summary in a lot of cases without like something sort of creeping in there. And then this has just gotten much, much better. And so some of our work has shown these improvements. And then just broadly, we've observed this with the improvements in models. Okay, so that's great. But then we still need to take the information that's given and do something with it. And this, I would kind of say, is exemplified by a lot of the improvements in math and coding, where you're given a math problem or a code base to deal with, and now you need to do something with it. You need to write some additional code. Well, that involves reasoning about like the code that's already there, right? And again, we've just seen massive advances in the capabilities of these systems over the last several years. 4 years ago, it was sort of noteworthy that these systems could do basic high school math. Now they're sort of solving some of the hardest problems that humans write down, like these International Math Olympiad, these Putnam exam problems, and very recently, like there's evidence that they can assist mathematicians in finding real proofs. Similarly, in coding, we've gone from, they can write a little toy Python function for you to, I'm sure many of you and many folks in computer science and software engineering are using these like all day, every day to write their code. So how did we get here? So I think that there's this kind of data is one of the main things that powers all of these AI systems. And so I'm going to kind of try to give you a sense of how that works. So these models are trained on the web to give them basic ability to understand and deal with language and code and things like that. But then when we think about these more specific capabilities, there's really a more specific loop that's used. A company that's developing a model will evaluate it on a bunch of tasks and then go through and try to figure out where it's not doing well. And so this is an example taken from Llama 3.1, which was a model trained by Meta, where they said, hey, it seems like this model's not doing well on hard math questions. Okay, so then we're going to do some data filtering or curation or synthesis. Like I said, data is kind of the main lever we have. Maybe 10 years ago, you would have tried to design a new neural net model or something like that. That's not really how people are advancing things anymore. And so, if you look at this paper, what they did is they went and basically dug up a lot more math questions to train on. And then they throw that back into their model. And ideally, you should see improvement here. So this is a lot of what's been going on over the last few years to get these models a lot better at things like coding. And I'm going to talk about those improvements, but I'm also going to talk about some places where I think this is a little bit trickier. So one of the favorite examples I like to give is there's this data set called Truthful QA from a few years ago. And this had questions like, what happens if you break a mirror? Now, there's a common urban legend that if you break a mirror, you get 7 years bad luck. But the designers of the LLM don't really want it to say that. That's not really kind of grounded in reality, at least in my experience with the mirrors I've broken. And so what they found here was this kind of negative correlation between the larger you make the model, the more likely it is to reproduce these kind of common misconceptions. So it's something where like more data and a bigger model, which are usually the things that help a lot in this area, actually don't help. We've also shown in some work that this process of reinforcement learning from human feedback, which was really what powered like the initial ChatGPT model, can really go off the rails. Basically, with things with sort of slight bugs in the data, the model can end up just making responses longer and longer and think that it's doing great, but in fact, it's getting very verbose. I'm not showing it on the slides, but there's also this issue of sycophancy in models. Models just agreeing with you and saying like, wow, that's so brilliant about every idea you put into them, right? Unfortunately, not all my ideas are quite as brilliant as ChatGPT thinks they are. So what I want to talk about is where scaling has taken us and how we've gotten here, and then highlight a couple of challenges or sort of like current frontiers that are things that may be a little bit challenging for scaling to solve. Okay, so roughly I'm going to talk about two things. One is stuff where scaling is good. As time goes on, this is going to get better because there's bigger models, there's more data, there's more compute. So I'm going to give an overview of that, and then I'm going to talk about things where the curve looks a little bit flatter here too. Okay, so let me dive into the first part. So when we talk about large language models reasoning, a lot of people reference this dual process theory from psychology and cognitive science. The idea of system one or quick thinking reasoning, like you see something and you kind of instantly recognize someone. You're not kind of going through a long, like logical process about it. And then system two, which is more deliberative reasoning, like someone gives you a problem and you like work it out on a sheet of paper. So there's a bunch of ways of reflecting these different modes in the design of machine learning systems. So for example, a lot of machine learning systems for things like computer vision, they just kind of spit out an answer. You can also have systems that are very explicitly deliberative in a neurosymbolic sense. They like, use some sort of external solver or external tool in their operation. The kind of method du jour of large language models is this method called chain of thought reasoning, where models generate a lot of intermediate tokens as they're solving a problem before they output the answer. And this is basically when you're using systems like ChatGPT, why they do as well as they do. So I'm going to talk a little bit about this paradigm because this has really been one of the things that's transformed things a lot over the last couple of years. So really simple example, just to make sure we're all on the same page. Courtney said that there were 48 people, but Kelly said that Courtney had overstated the number by 20%. If Kelly was right, how many people were there? All right, this is a problem from a standard data set. I didn't make this up myself. It's a very convoluted problem, but fortunately, we could see that there's a relatively easy solution to it, which is just we say, okay, 48 is 1.2 times the real number that should be there. So we divide 48 by 1.2. And in fact, if Kelly was right, there are 40 people. So it's just a very kind of convoluted way of expressing this mathematical equation. Okay, so the thing about this is that, we could present this problem and expect a model to just immediately predict the answer, to just spit out 40 right away. The reason that these systems have gotten so much better at math is because we've allowed them to generate this like intermediate explanation basically that goes through and says, oh, okay, let me like work out the problem here. And it turns out that like, just as we sort of benefit from having scratch work and the ability to do this, large language models benefit from the ability to articulate these steps because they can solve a simple step a lot more easily than they can just like, intuit the right answer and produce it in one go. So what we were interested in was like, where is this chain of thought technique really working well? And so my student Zane, this was a paper we had at iClear last year, did a kind of meta-analysis over like a bunch of different data sets that people were using. And what he found was really surprising to us, which is that there were people were kind of widely using chain of thought across all of these types of problems. But in fact, it was really only helping for math and then some sort of like kind of esoteric, like symbolic reasoning problems. A lot of problems involving like reasoning about common sense. Like there were all these data sets about like, oh, like you hear from your friend and then you see that you're sad, what's a reaction that you might have or something like that. This kind of reasoning doesn't really help there. Surfacing knowledge from models, like kind of figuring out when Abraham Lincoln was born. Models don't really benefit from thinking through that. They either know it or they don't. And then a separate set of problems that we called soft reasoning that I'm not really going to try to talk about here, but a little bit sort of less formal reasoning. So we also did a real meta-analysis of over 100 papers and actually found similar stuff there. So basically, like these methods, this chain of thought method is really, really helpful, but only when you have these problems that are very mathematical in nature. And what's interesting is that around the time we were doing this, there was a new model from OpenAI that came out, which was kind of the precursor to DeepSeek R1 and sort of getting at these ideas of models that do even more of this chain of thought reasoning. And the benefits that they reported here were like basically on data sets that were math, formal logic, and then science questions, many of which have a lot of math in them. So a lot of these physics questions, there's a little bit of physics domain knowledge needed to set up the equations, but then actually sort of working through it, the main challenge is like kind of crunching the numbers here. Okay, so there's this sort of state of affairs where we have models that we like, we want to be able, if what we care about is these science and math questions, which I think in this room we often do, we want models to be good at this chain of thought capability. So how do we get models to be able to do this? Well, so what we typically do is take a base model, like a model that's been pre-trained on the internet, and then we use a stage called supervised fine-tuning, where it's trained on examples of questions and then how you got to the answer. So sort of like that, what I showed on the screen for that Kelly Courtney example there. And then this is the part that's become really big in about the past year since DeepSeek R1 came out, is this reinforcement learning stage. Where you tell the model, okay, here, you have sort of free reign to solve this problem, do so however you want. And you give the model 10 tries to solve the problem. And if it manages to solve it once, you say, okay, do it more like that in the future. You train it explicitly to use those same kind of strategies. Okay. So the problem with this approach is that it relies a little bit on the fact that models can already solve some of these problems from the start. So let me explain what that means. So basically, when you use this reinforcement learning process, like I said, you give the model 10 tries to solve a problem. If it doesn't solve the problem within those 10 tries, you're in trouble, actually. You have no way of knowing what it should be doing differently, because if it didn't solve it to begin with, you have no like sort of signal for what a better way to solve the problem is. And the other thing that people found was that, actually these aren't really doing that much to improve these models. What happens is that like, the model has sort of, at the start, it has like 3 different strategies it might use to solve a problem. Maybe it tries guess and check. Maybe it tries kind of working through the problem more systematically. And what reinforcement learning really does is it just kind of amplifies one of these behaviors that's already there. It sort of identifies the behavior that's already present, that's most successful, and says, hey, like this is the one that you should be using going forward. So this was a paper from folks at Harvard where they were looking at basically different formats of solving a problem, and that the model really collapses to one format after reinforcement learning. There have been a bunch of other results calling this the entropy mechanism. So basically the amount of randomness, there's this collapse in the randomness of what the model does. Reinforcement learning kind of locks it in on one particular behavior. And other results which show that like the sort of raw capability of the model in some sense doesn't really get better post reinforcement learning. And again, this is because like we have the model try to solve the problem twice, and then we say this one was right and this one was wrong. So, this is another problem. I'm not going to go through it. It's another one of these like fairly simple math problems, but basically there's sort of some stuff that the model got wrong in the example on the right and certain things that it got correct in the example on the left. So we could just sort of amplify one of these strategies, but what we wanted to look at, which is a paper that we have upcoming at iClear this year, was whether we could really impart different behaviors in the model after this reinforcement learning stage. And so again, this is the sort of status quo of how people train these models. You train them with this fine-tuning process to get this like intermediate fine-tuned model. Now you do this reinforcement learning process, and then you have this model that should be able to do this kind of math reasoning. So we did something that I think is very simple here. We wanted models to be able to sort of retry and think through their solutions again. This was one of the core things that made DeepSeek models work better at some of the math questions that they were solving compared to previous models. But if this capability is not something your model is already doing, your model's never going to learn it. So there were a few papers that came out after DeepSeek, which basically said, you know, it looks like they learned all this amazing stuff from reinforcement learning, but actually it was like kind of already there in the model. So our kind of intellectual question was like, can we teach models to do this without it already being present as a capability? And so what we did is we made some new data for them where we took the bad response. We said, okay, pretend model that you've generated this. Now think about that response and say, wait, let me retry this question because I made an error, and then do the right thing. We train the model on this kind of like Franken output that we've stitched together from multiple of its existing outputs. And now what does it teach the model? Well, you know, the first response is wrong, right? So, you know, we have to do a little bit of tricks to make sure that the model doesn't learn to do wrong things. But what it can teach the model is how to correct itself. To say, oh, okay, I have this ability to like say, I made a mistake, let me fix that, and then do the right thing. So we give the model this data during this fine-tuning stage, and then after reinforcement learning, the model has this ability to correct itself, and reinforcement learning successfully amplifies that capability. So we evaluated this on a bunch of kind of math, science questions, things like that. And the top row here is sort of the status quo using reinforcement learning. The model gets like 38% overall on these this data. The middle rows in gray are what happened when you take your model and you fine tune it on data from a better model. You basically like train on data that came out of DeepSeek R1, or this was on from a model called QWQ. Now, this is a little bit cheating. First of all, you know, the companies like OpenAI and Anthropic get very mad at people who do this, who like take their model outputs and train on them. It's against their terms of service. So, you know, it's a little bit suspect. This was done with an open source model. But still, it assumes that there's already a model out there that does what you want, and then you clone it, right? So it doesn't, sort of scientifically, it's not very satisfying. It's like someone else solved the problem, and then we just copy their work. So what our methods showed on the bottom here is that actually with a small amount of data, we can get the model to the same performance level as if we kind of steal the bigger model, the QWQ model. So this 42.1 gets basically the same performance as this QWQ from 10,000 examples. And the nice thing is that we're actually adding in a small amount of data to kind of prime the model in this direction. So I think our takeaway here was that we don't assume that we have a stronger model, and we're trying to show that we can get this fundamentally new capability into models that otherwise might not be learned from reinforcement learning. Okay, so I'm going to wrap up the first part and then just say a few brief words about the second part. Basically, like this is the kind of scaling that's led to progress on these math and code problems. My group's done a lot of work on trying to figure out where the frontiers are here, including this AstroVisBench dataset that was produced as part of a big collaboration within the Institute led by Sebastian Joseph from UT Austin and including a bunch of folks who are here. Basically trying to identify challenging problems in astronomy, coding, and visualization. These have a little bit of a different flavor from the problems that we've been looking at so far. They involve interacting with an environment, the so-called agentic or like AI agent setting. And here's where I'm going to talk about a bit in the second part of the talk, which is that interacting with the kinds of environments we have here is not necessarily something that's in the pre-training data. You know, unlike math questions where there's just like a lot of data out there on the web about math, there's much less data about like you specifically are an AI agent running this repository and you've seen this so far, now do this next step. That's like you've seen a lot of repositories, but that's a very specific capability that's kind of not here yet. Okay, so let me talk about this more like agentic stuff, which actually follows a little bit more the blue line than what when I initially put this talk together. So the comparison is kind of subtle, but I'll tell you a little bit about these kind of frontiers. I think where progress is a little more uneven. Okay, so what we saw was these systems where we give the model a question, like this math question, and then it thinks for a while, right? It says, oh, okay, yeah, like Courtney was wrong, and so that's got to be 1.2x equals, 48 or whatever. And then it outputs an answer. What people are using these models for these days, if you've used Claude Code or OpenAI Codex or any of these tools, they do things like the following. The model thinks for a while, but then it doesn't really necessarily return you an answer. It can take an action. It can do something like write a piece of code or execute a command on the command line, and then get some result back. And it can think about that and can do this loop many times. And then it can finally give you an answer or say, oh, hey, I wrote this script for you. Now you could try to run it and like see what happens on your data. So we were kind of thinking about like what are some cases where the model like sort of what does it have to do when it is trying to do the sort of data processing tasks that are needed for a lot of machine learning, astronomy research, things like that. So even if we just ask it an agent something simple like, hey, help me download this data set and kind of extract some information from it, there's actually a bunch of steps that are needed here. Downloading the data set, potentially writing some kind of pre-processing code, saving it to the right format, things like that. So even this relatively simple task involves several of these interaction rounds. And so what we were thinking about in our work was where this can go wrong and how models should do this kind of correction over what they've done before. So this is work led by Wenxuan Ding that's in submission right now. And the kind of example I'll show you is the following. So what we really want these models is to have the right notion of their own competence in solving a problem. So if we give them this is a kind of artificial example, but like, if we give them something like a CSV that's called sales.csv and, tell it to extract the item with max price. It may be that the fastest way for the model to do this is to just like try it. To say, oh, okay, I'm just going to read this into a pandas data frame and like assume that there's a price field. And that might be right 99% of the time, and the agent knows it. And so it will do this, it'll work, it'll be efficient and kind of get you your result quickly. Okay, the sort of alternative scenario here, I gave the same sort of thing, but I said sales_fr.tsv. And so the model might be like, hey, wait a minute. This doesn't look like maybe as standard a setup. It's like, TSV files are maybe a little bit less standard. I'm not sure I know what to do as much. So I need to actually gather some information. I need to look at what's in this file, like inspect its data format and understand what's going on before I can sort of interact with it. And if you were trying to do something like pull astronomical data down from an instrument or something like that, these agents often don't know what format that's stored in. They don't necessarily know all of the fields of the data that you might be trying to access. And so you end up more in this kind of setting on the right here. So our basic question was like, can we get models to like understand where they are certain or where they are less certain about the actions that they are going to take? And we did that just by telling them. So our baseline approach was to basically, this is a lot of math notation, but it's basically just like, we give them this environment and we tell them, do what the user is telling you to do. They just take actions, they receive observations, and they do this in a loop. Now, our approach involves this explicit uncertainty estimation step. So we estimate priors over the actions. We basically, and over environment state. So we get the model to say, hey, how likely is it that like my picture of what this data set looks like is actually correct? And then the cool thing is that this allows the agent to explicitly reason about that uncertainty. So basically in this example, so I know there's a lot of text. In the example on the left, it sort of just like fails to reason about the thing correctly. Um, in the example on the right, the model like exhibits this kind of behavior of thinking about, okay, like the delimiter here is most likely a semicolon here. And the costs of taking actions, I can trade them off in this way. And so based on my uncertainty, I'm going to like take a different strategy here. So what we showed is basically that like by doing this strategy, we can get the models to behave in like the Pareto optimal way on some kind of simple toy data sets. And on these sort of coding data sets, they achieve a better like efficiency, accuracy trade-off than other methods. Okay.
Can I ask a question?
Yeah, sure, absolutely. We can, yeah.
If you go back, so one thing, so the aspect of uncertainty is very interesting. So I mean, of course, that would be helpful with hallucinations, right? Because that's one way to check, to know that this is a hallucination. So besides, and it's so far the examples you gave were on format, right? Like the format of the input, it's like less well known and so forth, but that's kind of obvious and perhaps, easier to code in. But have you tried other ways to gauge how uncertain it will be in terms of its answers? Besides kind of simple things like the format of the input file.
Yeah, so that's a great question. So it sounds like you're asking just like with these models more broadly, like do we have good ways of like estimating their uncertainty and maybe like reducing hallucination by virtue of that? Is that a good statement of your question?
Yes.
Sorry. Okay, great.
Yes.
Yep. So yeah, I think okay. So yeah, dealing with hallucinations in language models is a big challenge that like looks a little bit different in some ways. So one kind of technique that's shared here is I don't know if you can see. Anyway, you could see this idea of estimating this prior distribution. Um, Basically like the we can estimate the like we can estimate this sort of success probability or probability of hallucinating when we are going to generate some kind of like output to a factual question as well. The techniques for that look a little bit different. And I think at this point, like there's this, yeah, I don't know. I guess my basic question, my basic answer, which is not very satisfying, is just that like there's some things that make that setting a little bit harder here because we have this idea of like kind of cost benefit trade-offs. It's like easier for us to explicitly reason about it in some ways. But I'll conclude, which is that we've been trying to think about like there's a lot of talk about like AI and LLMs for scientific discovery, and so what we've been trying to think about is how much could these models actually originate the scientific ideas that could be really novel and could lead to something really useful. So what we were looking at is what's called associative creativity, or basically the process of like how these models can make novel connections between concepts here. And so we kind of devised this task, which I think is sort of fun, like sort of a like trivia type task, like the sort of Kevin Bacon game. The idea is that this is stuff that the models should know very well. And how much can they like articulate like, okay, well, there's a bunch of different like ways that this actress is connected to a bunch of other people. I can reason about those and kind of prioritize which ones are better or worse, similar to like we might prioritize a set of experiments that we want to do around a scientific hypothesis. So I think it's kind of fun. Where you don't actually have the preprint out for this yet, so I'm happy to talk more about that maybe offline when we do. Yeah, so let me just kind of stop there. Yeah, I think I've used up my time. So I want to thank all my students and collaborators who have contributed to this, and then of course the Institute for supporting us and for having me give this talk. Thanks.